Verification Corner!
Hello, welcome to Verification Corner. My name is Rustan Leino. Today we're going to look at verifying a little program that takes a little bit more effort to verify, but it's a nice example because it makes use of functions, makes use of ghost variables. We're going to see some places where we need to help the verifier along a little bit by providing assertions as lemmas and also breaking out lemmas as ghost methods. Let's take a look. Hello, I'm Rustan Leino.
And I'm Jason Koenig.
Jason, you've been my intern here this summer, working for about 3 months on various things. Could you say a little bit more about what was your background before coming into the internship, and what have you been working on?
Okay, well, I am an undergraduate at Carnegie Mellon University, and this past semester I took a freshman level course on introduction to programming, etc., but it talked about specifications, and it used dynamic specifications, which are dynamically checked at runtime. And I came here to work on static specification using the Dafny system. So these past 3 months I've been working on translating some of the programs from that class into Dafny, as well as extending Dafny in various ways. So.
Great. And we're going to take a look at verifying one program that includes a number of features that you've used a lot during the summer. Shall we take a look?
Yes, let's take a look. So today we're going to work with a binary counter, and this is going to mirror very closely the way computers represent the natural numbers internally. So what we're going to use is we're going to use a sequence of booleans in Dafny to represent a value, a natural number. And we're going to use a couple functions that I have here already typed in that are going to help specify this. So the first function we have here is pretty perfunctory. It's just the power 2 function, and it's defined recursively in terms of itself, and it behaves just like 2 to the n that you would expect from mathematics.
Excellent.
And the second function is what I call the value function. And this is the function we use to turn a sequence of booleans into a native Dafny natural number. So as you can see, it takes the sequence and as well as a base value, and this represents the multiplier on the value of the sequence. So if we pass in 1 as the base, then we get the standard definition of the natural number according to that sequence. And this has a kind of a complicated definition with a couple of cases, but things to note is the empty sequence is a zero value, and that the use of this base parameter lets us define this function recursively in terms of itself. So like the power function, this is also a function which is recursive. So we can.
So the leading zeros play no role, and we can see that as you recurse for the valid function, you're shaving off the first element, and therefore the multiplier has to go up by a factor of 2.
Yes, because the multiplier goes up because you go to the next base, the next digit in the number. So you have a larger base at that digit position. So one thing that's kind of backwards about this is that the least significant digit of the number is actually first in the sequence. And if you write out the sequence, it's actually backwards from how you normally write a binary sequence. So for example, if this was a sequence of numbers or Boolean values, 0 being false and 1 being true, this would actually represent, this would have a value of 1, this would have a value of 2, 4, 8, and 16. So this number here is actually 26, because it's 16 plus 8 plus 2.
And what are we going to do with these numbers?
So we're going to actually write only one method that manipulates these numbers represented as sequences. We're going to write the increment method. So I'm going to write the specification for this method. So we're going to have a method, and it's going to be an increment method. It's going to take a single sequence of Boolean values, which is going to represent the number that's input, and it's going to return another sequence, which is going to be also of Booleans, which is going to represent the result of that of the method. And what we want to do is this increment method should add 1 to the sequence that it's given, and the sequence returned should have a 1 greater value. So we can represent that with and ensures on the method. So we can ensure that the value of the result, according to the standard definition, is the value of the sequence we're given plus 1.
So here we have a post condition that says that the inc method will return R in a state that where it represents the number that is 1 higher than the input sequence.
Yes, and then that's all the specification we need, because every sequence is a valid number according to this scheme.
Great.
So.
Now, whenever we write a specification like this, we always wonder, is this specification all we need? Is this specification correct? Could we test this specification to make sure that it really is the specification we want?
Well, actually we can. So just given, we haven't given the method a body yet, so we haven't actually given an implementation that achieves this goal, but we can test whether or not it does by using it in another method. So we could have, for example, a main method that uses this function, and then we can use assertions to check what Dafny knows about the function, or about the method's behavior. So we can create a variable, let's say it's the empty sequence, and then we can assert that the value of this variable, according to our standard definition here, is actually 0.
Excellent.
Right? And then this checks out. So we can also then use our increment method. So we can increment the value of v, and then we want to assert that the value of v is 1.
Excellent. And it's interesting to note here that all of this is done statically. That is, we're not actually running the program. We're just letting the tool analyze the program for us. Actually, since everything has been so perfect so far, could we just for a moment change one of those assertions to the wrong value, just to see that we do indeed get an error message?
So yeah, so right now if we were to change the second one, like this is not true, and we see here that we do get an assertion violation. So Dafny is telling us, hey, that doesn't hold because it's not true.
Excellent. Okay, so now we have tested our specification with the main program a little bit, and we feel confident that this is the post condition that we want. So maybe now we should implement the method?
Okay, yeah, so now we can actually give this method a body. This will be the implementation that will actually give us the right result for the given input value. So we can, so the basic algorithm we're going to use to increment our method, and now Dafny is complaining about this because it doesn't hold. Before we weren't giving a body at all, now we're giving an empty body, and so it doesn't like that. So the algorithm we're going to use is we're going to start at the least significant bit, so start at the beginning of the sequence, and we're going to look until we find the first 0. We're going to set everything that all the ones that we skipped over, we're going to set those to 0, and we're going to set the 0 we find to 1. And we can see here we have the 26 we saw earlier. If we use this, we see the first 0 is actually the first digit, so we change it to a 1, and this value is then 27. So this is the increment by 1.
Okay. What if we do that again?
So if we do it again, we see, well, we increment a 1, we change that into a 0, and we keep going because we have a carry when we do our addition.
So just like we did in grade school.
Yeah, so it's a grade school carry addition, and it's a special case of only adding 1. So you don't have to worry about carrying multiple digits or anything. There's only one thing to carry. So then we carry it, and then this was the first 0 in the original number, so it gets set to 1. And then this is 28.
What if we scan it and we never find a 0? Because, for example, maybe all of the bits are all 1 in the number.
So if we never find it, we can use the fact that there's an implicit 0 at the end of it. So we can just add something on and then make that a 1. Excellent. So the representation, the sequence doesn't necessarily have these zeros on the end. So they're implicit in the representation, but we can make them explicit and then set them to 1.
Great. Let's take a look if we could do that in code.
Okay, so in code, this should suggest a while loop, and for any while loop we need a variable to iterate with. So we're going to iterate with the I variable. We're going to start at the beginning of the sequence, and then we're going to do a little while loop. So while we haven't fallen off the end of the sequence, we're going to iterate. Now I've introduced this variable r here, and r is going to be the result of our computation. So you can see it's in the return value is this r, but when we start with the method, we actually don't, r isn't initialized to anything. So we should start off with the initial value that we're given, and then we're just going to modify that throughout the method.
Mm-hmm.
Okay, so so among the things Dafny is complaining about is that we actually don't terminate this loop, and that's because I isn't modified. So we're going to want to go through the loop and increment I as we go through it.
Mm-hmm. And then we might as well write an invariant about that I to say what the range of it is, as we often do in verification.
Yeah. So every time you see one of these little loops, it's almost always going to have an invariant. In this case, our invariant is just that I ranges over the elements in R.
Mm-hmm.
So
starts as small as 0, and it could be as large as the length of the sequence itself. Excellent.
Yes. But this isn't quite everything, because we only iterate until we find the first 0 in the sequence. So we have to actually iterate not just that we haven't fallen off the end, but also that we are still seeing a 1. So we have to say R at the index we're looking at is actually equal to true, which is representing 1.
Excellent.
Okay. So this currently just looks through it and finds the first index, but doesn't actually do anything once it gets there. It doesn't modify the sequence at all. So the first part of our algorithm, as it skips over these 1s, it sets them to 0. So we're going to do that here in the loop by setting R to the sequence R with the index I set to false, which represents 0.
Mm-hmm.
So this syntax means that we take the sequence R and we set the index I to false, and then we assign the result of that back into R.
Excellent. So now we have a loop that goes from the least significant digit to more significant digits, and whenever we encounter a true, that is a 1, we set it to false, and then when there are no more such, we stop the loop.
Mm-hmm. So and then we have one more step in our method, which is we have to increment or to set the bit at the last bit we find. So we have to turn that 0 into a 1. And there's actually 2 cases for when we have to do that. And one of them is the one Rustan mentioned before, which was that when we get to the end of the sequence, we actually have to add something onto the end. So we're going to set R to the value, and we're going to use an if statement, which is like a ternary operator in other languages, in order to accomplish this. We can actually distinguish the 2 cases based on the value of I. So if I is less than the result of the sequence, then it's somewhere in the middle of the sequence, and there's an actual 0 bit there that we can set into true.
Mm-hmm.
So we can just take R and at the index I set it to true. Otherwise, we have to add something onto the end of the sequence, and we can just add true, because if we add 0 and then change it to true, it's the same as adding true. So we're just going to add the singleton to add a single true on the end.
Excellent. All right. Let's see. So does that mean that we have now proved the program correct?
Well, as you can see here, we've got a problem with the post condition. And the problem is that even though this code is correct, it's not actually enough to convince the verifier that it computes the right result. So it doesn't know that all of these, you're making a lot of different updates to the variable R, and it doesn't know that the value is actually the correct value. So we're going to have to add some more specifications, some more constraints on what the program can do in order to convince the verifier that we're correct.
So we're going to describe something about R with each iteration.
Yeah, so the first part of it is to verify that what the loop does. And right now we have almost no information about what happens in the loop. So the loop could theoretically set R to the empty sequence or all sorts of things. So we're going to want to figure out what the loop actually does to R, and then encode that in invariants in the loop.
Mm-hmm.
So what we notice about this is we're always setting something to false, right? We're always going through and we're setting the initial values of the sequence to false. So if we look at what happens at each step of the loop, we're actually decreasing the value of r by the value at that position. So if we turn a 1 into a 0, and it's at the position with value 4, then the value of r decreases by 4.
So that means that eventually we'll have to add something even bigger to r than just the 1, because we've decreased it as we've gone along through the loop.
Yes. So to keep track of that, we're going to introduce a ghost variable, which is a variable that's not necessary for the code, but it's used for the specification. And this is going to be inc amount, which is the increment amount that we have left. So initially, we have to increment our value by 1. But as we go through and we set things to false, we're increasing the amount we have to increment by. So later in the program, we're going to have to add more back in because we took some off initially. So we can write another invariant that says the value of s, comma 1 is the old value of r, because s hasn't changed. S is never modified in this program. So this is going to be the old value, and we're going to say that plus 1 is our goal, right? And you can see in the post condition here, that's the goal value that we want it to be. So we're going to say that's going to be equal to inc amount plus the value of r. Right.
And so this is invariant through every iteration of the loop, which means that any time that we decrease the value of r, we also need to make it some change in the inc amount.
Yes. So here, every time we set I to false, we have to actually increase the amount of the inc amount because we took something away from r, so we have to add it in to this other side to keep this equality true. So what we notice here is that the value of I, at position I, is actually 2 to the power I. So what we can do here is we can say inc amount is equal to itself plus the power 2 function at I.
So as we change a true bit to false in R, we're then incrementing inc amount by the corresponding integer amount, which is the power of I, right? Good. Then we could write an invariant, if we wanted to, that said that in every iteration through the loop, inc amount is in fact the power of I, because
yes, we could, because if you notice in the initially, inc amount is 1. So that's 2 to the power 0. And each time through, it's added, if it starts off as the power I, then when it's added to power I, it becomes power I plus 1. So that's actually, that invariant is preserved. And we can write that down and check it using Dafny. So Dafny will actually take a look at this, and it will tell us that that invariant is satisfied. So that and that can help us prove other invariants, because that's a pretty strong property of inc amount.
But it still has some complaint about the invariant that we're trying to maintain here, that uses inc amount. Maybe it needs more information than about the values of other variables. And inc amount it knows all there is about, because we say that it's equal to the power of I, but maybe it needs more information about r.
Yeah, so what we need to know about this is that when we set this to false, that the value actually falls by power I. Right? That's the critical value, the critical piece of knowledge that it needs, is that these two things, when inc amount increases, then value r decreases by the same amount. And if it knows that, then it will be able to prove the program correct. So we can encode that. We have to give some properties of how these variables work. So one thing that we can do is we notice that when we set these things to false, everything that we've already set to false is still false. So we might want to encode that as another invariant. So we say for all indices k, k being index that's less than I, then the value of r sub k is false.
Right.
So this says everything that we've looked through is already is still false, essentially. And then this lets us understand more about how the variable r changes. So the other thing we need to do is introduce a lemma which talks about how we can split the variable r around the point where we modify it. If you look at the value function, the value function is defined in terms of the start of the sequence and also the rest of the sequence. So in order for Dafny to understand how it changes when you modify the middle of it, you have to split it around that point.
So the definition is recursive and does not directly speak about something in the middle, so we'll have to somehow get that property, and you're proposing we write a lemma for that.
Yeah, so we need a lemma, and lemmas in Dafny are ghost methods. And this one, let's call it the splitting lemma, because we're going to split our value at a certain location. So we're going to split our sequence of booleans, and we're going to split it at an index I. Okay, and we're going to require a couple things about these, about the sequence and the index that we're going to split it. So we're going to require that the index is actually a valid index into the sequence as far as splitting it into two parts is concerned. So it has to be somewhere in the valid range.
So dividing point. So it could be, again, as small as 0 and as large as the entire sequence.
Exactly. So the other thing that we're going to require is that everything before I in the sequence is false or 0.
Which is exactly what we have in the loop. That's nice.
Yes. So that turns out to be the property that's common, is we have a bunch of zeros and then some value. And we always modify our sequence starting with a bunch of zeros to the left of where we modified. So this is actually perhaps not the most general lemma, but for our purposes it will work. So we write the same quantifier as before, where we say for everything in that range up to I, but not including it, that the value there is false.
Excellent.
And what we need from this lemma is that the value of the entire sequence S that we're given, so we need to talk about the value S according to the standard definition, we need to say that that is equal to the value of everything past S, but it's no longer just the value there. At 1, it's now the power of I.
I see. So since all of those least significant digits are zeros, if we just consider the value from I onwards and then use the power of I as the multiplier instead, the two should be the same, is what the lemma says.
Yes. So that's what the lemma says. And this is actually turns out to be very useful in when we're incrementing something or de-incrementing something, because when we talk about value of Si ... we talk about S with I and everything past it, and we can split that. Now when we modify the index I, we can split that as the first element of that subsequence and then the rest of that subsequence. And then this talks about how that relates to the total sequence. So if Dafny can figure out how we modify this subsequence, it can figure out how we modify the value of the whole sequence.
Excellent.
And this is why this lemma is going to be useful for us. Okay.
So how do we use a lemma then?
So a lemma it's a method. It just happens not to be compiled into the resulting program. So when we take this lemma and we put it into the program, we can just call it as if we would call any other function. So we can call it the splitting lemma. In this case, we're calling it on our variable r with index I. So we're going to split the current state of the counter around the index I where we're going to modify it. Okay.
And so since we modify r again after the loop, do we want to make use of the lemma there as well?
Yes, so we want to take this lemma and we modify r at index I here as well. So we want to take this this lemma, and we also want to put it at the end of the method, and that will take, using these invariants, it will be able to prove the post condition. And it turns out there's actually one more invariant that we need, which is that the value of r at 1 is equal to the value of r at the subsequence at power I.
Which resembles the post condition of the lemma.
Yeah, so it's basically the post condition of the lemma, and as you can see with that invariant, we get and the lemma at the end of the method, it actually proves the post condition. So now what we have is that the invariants are strong enough to prove that the post condition holds. So now we know our invariants are actually strong enough to prove the post condition.
But it seems we still get some complaints here about the invariants. What are we going to do? It complains that that one of the invariants might not hold an entry and the other one is not maintained in the loop. Are there more properties that it needs, perhaps?
Okay, so the first one we notice here is that the value of the rest of the sequence, this one is not it doesn't know that this holds on entry. And the reason it doesn't know that is because it doesn't actually know that at r and r of I dot dot are equal. So if we can tell it that via an assertion, then it will figure out that value is actually true. So now once we tell it to find that, it can prove it just fine. And then it can use that to prove the invariant. So this is an example of sometimes where there's a property that it can prove on its own, but you need to tell it that it needs to prove that in order for it to use it later. So it won't figure out necessarily that it needs to do it on its own.
Right. So in general, with an automatic verifier, there are many properties that it knows by itself, and there are some properties that one can poke it to prove, and then it knows to prove them. And in Dafny in particular, sequences are an example of that. That especially when you split up a sequence in different ways, like with these operations that take only the elements from some index onwards, for example. And so here we have what seems like a very simple property, but since it relates to sequences and ranges, we may know that we need to supply them manually. Maybe a better version of a prover in the future would do that automatically, but here we supply it.
So these provers are always getting more and more powerful in the number of things that they can handle. And the main problem is if they're able to handle too many things, and they just get confused and they get lost down blind alleys that never lead to anything, and it becomes very slow to verify. So part of the advantage of having to get the speed, you really need to limit some of the things that it can do on its own. And that's true in this case. So we have one final problem, which is that this invariant is not maintained by the loop. So it knows that it holds on entry to the loop. It just doesn't think that the method body or the body of the loop actually keeps the invariant true. So we're going to have to give it a little bit more of a poke to tell it how to reason about that. And really what we have to do is we have to expand, or we have to tell it how to split R, and actually a subsequence of R, into the right values. So we're going to do that again with another assertion, and we're going to assert here that the rest of the sequence, past I and beyond, is equal to the value at R I, the value at Ri plus no, it's so we want to actually do Ri minus 1 and then Ri minus 1. So we need to tell it how to split this the sequence into the first element and everything beyond that element. When it sees that split, what it can do is it can it can use the definition of the value function on that splitting, and it can break it into the first element and everything else, and then it can reason about how the value of that changes. In this case, Ri minus 1 is the old value of I, so here Ri minus 1 is the value that's changed. So this is telling it how to split the value, specifically split the subsequence of I and everything else.
So this assertion is similar to the one that we needed just before the loop, then, in that it instructs the verifier to prove some properties about sequences that it knows if it only knew that that's the property that it should go and verify. Excellent. So it seems like we have no complaints here, but let's see what we have done. We've introduced two assertions. Now, an assertion is verified by the verifier, and then afterwards it can be used by the verifier. And we've also used the lemma. So the lemma means that we can make use of that property, in this case, in two places in the program. But what says that the lemma is true?
Well, so in general, lemmas require proofs as well. So lemmas aren't just freebies, right? You have to give a proof. And for our example, you can see we gave a proof of the properties here by writing some code that used the right invariants, and that's how we proved the property of the post condition. And lemmas are no different, except for all of their code is just for the purposes of specification. And the lemma that we have here, the splitting lemma, has no body, which means right now Dafny's just assuming that it's true. And it turns out the proof of this lemma is actually quite involved, so we won't have time to do it here. But
maybe a different verification corner can focus on just how you prove lemmas.
Yeah, so we can look at that in another verification corner, and if you look at the code on the website, it will have a proof of this, so that it will be fully verified, and you won't have to trust any of our assertions about how it works.
And in that case, the only thing you have to trust there is that the specification is the right one, the post condition is the one we want, and we tested that in the main body to at least give some cases for that we can see that it gives us exactly what we want. Excellent. All right, let me summarize what we've seen. Jason proved a program that deals with some properties of sequences and integers. And to prove the program correct, we needed not just loop invariants, but as usual, but also ghost variables, some properties of them, and some lemmas. And we saw lemmas can be written either as assertions or as broken up into ghost methods, which are, when they're compiled by the compiler, just go away. That is, they're just to prove the program's correctness. Now, what we left out was the proof of the lemma itself, which again you can look at the code on the website and come back to a different verification corner, and we'll show you how to prove lemmas. So you've been watching Verification Corner. I'm Rustan Leino.
And I'm Jason Koenig.
Program
safely.
Verification Corner.